but there are some material we intentionally left for discussion. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Allahumma sholli ala sayidina Muhammad wa ala ali sayidina Muhammad. Allahumma fir lana wa li walidina warhamhuma kama rabbayana shighara. Allahumma innaka afuwun tuhibbul afwa fa'fu anna. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzabannar. Rabbi shrali sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Rabbi zidni ilma warzuqni fahma. Amin ya rabbal alamin. Fisika unsur, I think you have to turn off your background filter so we can see your face.
Yes, Dr. Fabian.
Yeah.
They are still arranging.
Meanwhile, Rico, can we take picture together?
Yes, sir.
So guys, please turn on your camera. Oh, Naufal, thank you, Naufal. Gaby, thank you. Before that, I see Sania. Sania, terima kasih.
Slide 1, 1, 2, 3. Slide 2, 1, 2, 3. Sudah, Pak.
Okay. All right, guys. Without further ado, let us continue our material on density functional theory. And like what I just said in the beginning, it will be our final straw. But you will find in the end that I will not finish everything. I left some materials for us to discuss in the class or amongst yourself. Like usual, let us see what do we have so far. And some of you perhaps will ask, why do we have to repeat last week material? Always like that. Well, I just remind you about our favorite backstitch, jurus tikam jejak. When I was in elementary school, in the second year of my elementary school, we got a lecture how to menjahit, to stitch. In my junior high school, we make cloth. I make piyama during my junior high school. So in my time, I know how to stitch my clothes. And one of my favorite stitch is back stitch, jurus tikam jejak, tusuk tikam jejak. You have to go back every time you already in this stand, and then you have to go back and then make it further. It is always like this. And in education, this method is the best way to teach the heavy material, the difficult material. We have to repeat. So if we have like 2 hours class, 1 hour is just to repeat what we discussed last week. If you don't believe me, ask Dr. Mark. He is also in the old generation like me. Right, Dr. Mark? Please say yes. So that's why in my class, if you know me well, like Naufal knows me well, I always repeat my material because it is difficult material. If it is easy material, we don't need to do this, wasting time. Anyway, let's go to the first slide. The need of quantum theory. In chemistry, there is a question, long question. Why the double and single bond have the same bond length in conjugated system? Our previous example is ozone, but not only for ozone, for any molecules that have, the alternate bond, a single and double bond. Remember the song? Single bond, single, double bond. That's conjugated system. Yeah, Tika, do not laugh. These questions cannot be answered unless we use quantum theory. Not only in chemistry, in physics, we also have 2 problems that also need quantum theory. First, why light can push electrons in the photoelectric effect, 1905. Einstein explained it using quantum theory. Why? The second problem is why electrons can interact with itself and create interference patterns. Davison-Garmer experiment, 1923 until 26, exactly like what wave does. Thomas Young experiment 1801. 1801. Like 300 years ago, almost 300 years ago. Almost 300 years ago, and Thomas Young is still young. It is like kacang panjang, kacang panjang, you cut kacang panjang into several pieces, and each pieces is still panjang.
Bukan karena
Alright.
nggak bisa.
What is quantum theory? First, let's see what is classical mechanics. When we study particles or waves, I distinguish the color. For particles is red and for waves is blue. When we study particle using particle equation of motion, and when we study wave using wave equation of motion. So that is classical mechanics. And this is the foundation. This is the foundation of causality principles, or what we call common sense in physics. Okay? Causality principles or common sense in physics. If I hit you, you will say, aduh, that's causality. And you will be angry. That's causality principle. So I said it again, causality principles requires the classical mechanics. Or the classical mechanics is the foundation of causality principles. In quantum theory, we switch the mechanics. When we study particle, we use wave equation. When we study a wave, we use particle equation. When you do this, the causality destroyed. There is no common sense. So there is no philosophy in quantum mechanics. There is no philosophy in quantum mechanics. In classical mechanics, we do have philosophy. But in quantum mechanics, there is no philosophy. So if someone approach you, hey, for example, Farah, do you want to be my follower? Because I have quantum mechanics philosophy. That's a lie. You have to run away from the guy like that. There is no philosophy in quantum mechanics because there is no common sense. Why do we don't have common sense? Because we do not use particle for particle and wave for wave equation. We do it the other way around. Because there is no common sense, so the result need to be interpreted. The results of quantum mechanics needs to be interpreted. Anyway, the mathematical formulation of quantum theory, that's what we call quantum mechanics. The mathematical formulation of quantum theory is quantum mechanics. And since there is no common sense in quantum theory, there is no common sense in quantum mechanics, that's why we need interpretation from results by quantum mechanics. Remember that well. Many interpretations, but the most interpretation that we use so far is Born statistical interpretation. Perhaps you know in Marvel universe, they have multi-verse. Stanley took it from quantum theory because one of the interpretation, Stanley is the creator of Marvel universe, because one of the interpretation of quantum mechanics is multiverse. So each time you have two options when you want to eat for your breakfast. Do I want to eat roti canai or sate padang? I cannot eat both because I am miskin, I am poor, I only can buy one. And roti canai is cheaper than sate padang because sate padang you need to import from Padang. Roti canai is, you can find it in any town, anywhere in Johor. Finally, in the end, you choose roti canai. But part of yourself choose sate padang. Then you create two universe. You create another universe that is also interpretation of quantum mechanics, and it exists, and you can find many papers try to use that interpretation for quantum mechanics results. Interesting. Yes, it is interesting. And you will find many fiction novel based on that interpretation. But unfortunately, in atomic and molecular physics, we don't use that kind of interpretation. We only use Born statistical interpretation. Boring? Yes, boring. So that's why move to Hollywood, use that interpretation to create a new movie. But you are too late because Stanley already did that. You know Stanley, right? All right. Schrodinger equation. One wave equation for particle is Schrodinger equation. Mathematically speaking, it is just a second order partial differential equation. The solutions of Schrodinger equation already exist long before the equation was born in 1925. So mathematicians already had that equation, but they didn't know how to use it. So they already have the solutions. Wave equation consists of time and spatial domain. Time, spatial. Spatial is volume or dimension, our room, space, spatial domain, which mathematically can be split into time and spatial domain equations. The time domain equation has a fixed solution. This is the solution. It doesn't change. It is always like this. While the spatial domain equation has a solution CR, which depends on the potential energy function. Now we have this kind of notation, function of function. We call it functional. We call it functional, function of function. Potential is function of wave function, while wave function is a function of position. Function of function. We call it functional. The spatial domain equation is what we call time-independent Schrodinger equation, or usually people abbreviate it by TISE. T-I-S-E. TISE. Okay. TISE is a n-body problem equation. N is equal to 1, 2, and so on. Or what we call it, one-body problem, two-body problem, three-body problem. And if we have so many n, we call it many-body problem. So time-independent Schrodinger is actually many-body problem equation. Time-independent Schrodinger equation can be used to explain many-body problem. Unfortunately, only one body time-independent Schrodinger equation can have exact solutions. So we have two kinds of solution in mathematics: exact solutions and approximate solutions. And before we go further, we need to understand what are exact and approximate solutions. So for that, I will share you an example. I will stop share and use another. Can you see now my mathematic windows, Dr. Lucia?
Yes, I can see it,
Yes.
Dr.
Yeah,
Fatima.
thank you. Yeah, this is a simple ordinary differential equation. Wait, something is missing, Dr. Lucia. I think you know what it is. This one is a simple ordinary differential equation. And we can solve it right away using any method you want to solve. Like, for example, I will use, this is Mathematica. Student of Johor, you can download Mathematica for free because I check in internet, you get the license. So you can download it. In Unair, we can do it anymore. We cannot do it anymore. In ITERA, in Unsur, also we don't have the access. But UTM, you have access. See, I will solve it. I will translate this equation into mathematical Wolfram language using like this, and let's see how it goes. You got the solution. Cos plus sin. All right. But we have, in physics, we have a pendulum motion, oscillation. And the oscillation, actually, this is the equation of motion for pendulum. And we have this function, sine as a function of theta, but theta is also a function of time. So this is also functional, which make the equation is non-linear equation. This is, before that is linear equation. This is not linear equation. What happened when we try to solve it using exact solution? Look, so I translate this equation into Wolfram language. Let's see what happened. This is not exact solution. This is approximate solution. In physics, usually we cannot handle this kind of problem. So what we do is we make some approximation. We make a declaration that the pendulum moves very small theta with a very small theta. When theta is so small, sine theta is equal to theta. When we have this approximation, then the equation of motion is like this. This is linear equation. There is no sign anymore. So when we translate this equation into Wolfram language like this, you can also use Python or whatever you want to use. And then straightforward, you got the solution, exact solution. So we have two kind of equations, one which have exact solution, and the another one, you need to make some approximation. Finally, you will get approximate solution. All right, let's go back to our slide. After you understand what is the exact and approximate solutions, now you understand that Schrödinger equation, These only has a solution, exact solution, if it is one body problem. Two body problem, no exact solution. Three body problem, no exact solution. Only one body problem of These has exact solution. Keep that in mind. All right, now we go to hydrogen atom. These must explain the phenomena of one, resonance structure, and second, electrons interference. Of course, in this class, we only answer for number one, resonance structure. Before explaining resonance structure, Dr. Lucia. Oh yes, it is me. I'm still here. I thought I missed my my video. Before we use These to explain resonance structure, These must be able to explain the most simple creature in the physical universe. V0. We usually call it V0. Just a constant, no longer function.